Hi, everybody, and welcome to the last installment of our equilibrium unit here. We're at the top of page 10, and we have titled our notes today, the external factors affecting chemical equilibrium. Now, I'd like to tell you that this is pretty common sense, so I'm hoping that you don't find too many issues with this. All right, you guys, we're going to learn about Le Chatelier's principle. All right, this tells us that if we have a particular stress, if we stress any kind of chemical system or chemical reaction, and we put a stress on it, then what's going to happen is that chemical system is going to try to reestablish its equilibrium. So if a stress is applied to a system that is already at equilibrium, the position of the equilibrium is going to shift in the direction that actually helps us reduce that stress. Okay, we're going to talk about below a couple examples of what that stress would be. Before we begin, though, let's go ahead and remind ourselves that a shift is going to occur to reestablish equilibrium positions. So a chemical reaction is going to shift based off of a stress that's been applied in order to reestablish that equilibrium position. And you guys already know it. Big case K, which is our equilibrium constant. Don't confuse it with lowercase k, which is what we saw in kinetics, okay? You know that the equilibrium constant is proportional to products over reactants. So let's go ahead and talk about what the potential for the first stress could be. And that is when we would add or remove something from the chemical reaction. So adding or removing a species in any particular reaction is going to cause the equilibrium to shift. And when it does so, it's going to do its best to shift in the direction that helps us reestablish the equilibrium constant, or K. Now, the analogy that I use here, and I hope you can excuse it, is I use the analogy of the mama cow. All right. A mama cow, by the way, is a mammal, and mammals have mammary glands. So when a mama cow gets pregnant and has a calf, she's going to produce milk for her calf. And yes, all mammals work this way. But here's the idea. You got the mama cow, it's producing milk. So long as that calf is taking or consuming mama's milk, the mama cow is going to continue to producing milk. Does that make sense? So once the milk goes to the calf, and as long as the calf keeps drinking, mama's going to keep producing. All right. So if you consider that general analogy, what we're saying here is if you, in any particular reaction, and let me go ahead and just write a generic one down here, A plus B equals C plus D. All right, take a look. If I take away any of these products, one of them, let's just say, for example, if I take away C, for example, then what's going to happen is since I removed the product C, the chemical reaction is going to shift to make up for that. So naturally, the reaction, if I remove C, is going to shift right to try to produce more of that so it could bring it back into the system to reestablish equilibrium. What if I don't know, removed A, so whatever species A was? Well, if I remove A, wouldn't it make sense that the reaction is going to shift to the left to try to make up for that? So that's kind of what this bullet point is saying. You can also add things. In the examples that I just gave you, we talked about removing things. Now, think to yourself, what if I were to add more of one of these species? Let's say I added more of A. What do you think is going to happen to reestablish equilibrium? If I added more of A, would it shift right or would it shift left? Good question. Why don't you think about that? And in a second, when we go to do some practice problems, you could revisit your thinking and, of course, or reevaluate your thinking rather, and see if you were right. Okay, so the first stressor was adding or removing something from a reaction. The second stressor that's discussed in Le Chatelier's principle is this concept of increasing pressure. Now, remember, guys, when we talk about equilibrium, we're really only dealing with gases and aqueous solutions. We don't deal with pure liquids and solids as a part of the equilibrium expression. So naturally, you're going to see something with gases here. So we're talking about pressure. It says increasing pressure will cause the equilibrium to shift to the side containing the fewest number of moles. The fewest number of moles. Remember, little n is moles, right? Well, one of the ways to kind of think about this, you guys, is say I have a piston or a cylinder and I have some type of plunger and I close that system off and there's some gas molecules inside there. What if I were to push down on this plunger, thereby reducing the volume inside the plunger? What do you predict would happen to the pressure? That's right. The volume would decrease and therefore the pressure would increase. So the rate at which those gas molecules are hitting the side of the container in the compressed version would have higher pressure. Okay. So in a way, when you think of increasing pressure, you might want to think of squishing, like kind of like you're squishing gas molecules. I know it's not too much of a technical term, but what's going to happen is if you're dealing with a reaction and you're increasing pressure or you're squishing the gas molecules, the chemical reaction is going to shift to reestablish equilibrium to the side of the reaction that has the fewest number of moles of gas. Okay, we're getting ready to do an example dealing with this in just a second. Okay, another thing that we should talk about regarding Le Chatelier's principle is what does adding a catalyst do? Well, it's kind of anticlimactic because really adding a catalyst to a reaction isn't going to affect the equilibrium of the particular reaction. In other words, I add a catalyst in, the no shift is going to occur because catalysts have no effect on the equilibrium constant. Now, remember, a catalyst will speed up a reaction and make it happen quicker, which you guys remember with kinetics, okay? And lastly, let's talk about temperature. What does temperature do to chemical reactions? What increasing or decreasing a temperature is going to obviously is a stressor, and therefore obviously will affect the equilibrium position. So let's take a look. In thermochemistry, we previously learned what an endothermic and exothermic reaction are. And I really want you guys to think of heat energy as a reactant or a product. Okay, so what do I mean by that? Here's your two types of reactions. We got endothermic and we've got exothermic. You guys remember that an endothermic reaction, that whatever we're defining our system as, heat energy is going into that system. So if you take a look at the generic reaction, A plus B yields C plus D. A and B are the reactants, and heat energy needs to go into those reactants in order to produce the products. So in an endothermic reaction, and you guys can see here that our enthalpy values are positive. Positive enthalpy values tell you that the heat energy that is being added is going into the system. That's what that positive value tells you. In this case, consider heat as a reactant. And you could see that it was written here as a reactant, okay? Now, what's going to happen here, you guys, if I actually attempt to remove that heat? Okay, it's a reactant, and I attempt to remove it. What do you think is going to happen? How do you think this reaction is going to shift to reestablish equilibrium? Well, if I try to remove the heat somehow, yes, you then guessed it right. The reaction would shift left to try to make up for that, or to try to replace it, if you will. Okay, well, an endothermic reaction, conversely, exit, heat energy is leaving the system. In this particular case, we always know that our enthalpy values are negative, and therefore that tells us that in that particular reaction, the amount of heat energy produced is going to be lost from the system, and of course it goes into the surroundings. You can see here that you consider heat as a product, and you could write it as a product. Now, in this particular case, can you think about what would happen if I attempt to remove heat from the product side? Which way would the reaction shift? Think about it. Let's do some examples. Okay, so we just went over the primary factors in Le Chatelier's principle. Stop, rewind, hear all of that again. Hear it twice and 3 times. It's that important. You need to know this stuff, okay? Let's go ahead and jump right into exercise 13. It says arsenic can be extracted from its ore by first reacting it with oxygen, and that's a process we call roasting. Okay, and it does that to form solid As4O6, which is then reduced using carbon. So go ahead and take a look at the reaction. You guys can see the double arrows there. And it says to predict the direction of the shift of the equilibrium position in response to each of the following changes in conditions. So I've got 3 scenarios here. It looks like A, B, and C in each case. They're adding, removing, they're doing something. They're either taking away or adding a stress to the system. So I'm going to need to figure out which way the reaction is going to shift. Okay. Now go ahead and do me a favor. Take a look at the states of matter for the reactants. They're solids. Oops. They're solids. You guys, they're not going to be a part of the equilibrium expression. So if I had to ask you, how would you write the equilibrium expression for this reaction? Don't you agree that it would be, simply put, right? So there we go. Think about which side of this equation is more ordered and which one's more chaotic. What do I mean by that? Well, if you looked at the left-hand side, the 2 species are solids, and after the reaction has occurred, they are converted to new substances or gases. Don't you agree that the side that would be more ordered versus the side of the reaction that would be more chaotic? Solids tend to have more structure. They're definitely more ordered. Or gases, they're just kind of floating all over the place, hitting the side of the wall, going off into every which direction. So, that's something to kind of consider when you're looking at actually in your mind's eye what is happening in this particular reaction. You can argue that the product side is probably going to be slightly more chaotic, and the reactant side's a little bit more ordered. Okay, so now we know what we're really looking at, and what we're really looking at is what is happening to these 2 gases. Okay, so then 13A is asking us, well, what if we add more carbon monoxide? That's this stuff right here, that species. So what do you think would happen if we added more of that CO2 to this reaction? Yep, adding more, and I'm going to go ahead and write down here in the margins. Okay, adding more CO2, or excuse me, CO, carbon monoxide, is going to cause it to shift left. That's right. I'm adding more of this stuff. And since I have a surplus of carbon monoxide, it's going to do its best to shift left to make up for that. Okay, to balance it out, if you will. So adding more of that product is going to shift it left, thereby balancing the reaction out so it can basically reestablish its equilibrium. And it will do that when it shifts it left. It's going to try to form more of the product, reactants rather, to again, to reestablish that equilibrium. Okay, B, what if I add or remove, all right, add or remove carbon or tetraarsenic hexaoxide? So those 2 are products, or excuse me, those 2 are reactants. And you can see, I just told you that both of them were solids. Okay, and we just talked that solids are not a part of the equilibrium expression. Therefore, they do not affect, I think it would be affect, the equilibrium. Okay. They're just not even part of the expression, you guys. Does that make sense? All right, let's do the last one. What if I removed that As4, that arsenic gas? So in this case, you're getting rid of something here. All right, and if you're getting rid of that As4, what direction do you think this reaction is going to shift in order to reestablish equilibrium? That's right. As long as I keep getting rid of AS4, it's going to shift right to make up for that. So AS4, it's going to shift right. Yep. So when it removes that product, it needs to form more of it, so it shifts it to the right. All right. Hopefully that wasn't too bad. Let's go ahead and do exercise 14. We're almost done here, you guys. All right, exercise 14. Predict the shift in equilibrium position that will occur for each of the following processes when the volume is reduced. So the key is, we just talked about pressure, remember squishing. If I reduce the volume in a system or in a reaction vessel, and I cause that squishing to happen, you guys know that pressure is going to increase, right? So generally speaking, this is going to be the context of our problem and how we're going to answer it. So they're reducing the volume. And so I look like I have A, B, C with 3 different reactions. And so in the back of my mind, I need to know, how is this reaction going to be affected if I reduce the volume in whatever situation they're describing? Okay. A, the preparation of liquid phosphorus trichloride by the reaction. Well, this one is the phosphorus trichloride, so it's important to know what they're talking about when you read these problems. Of stuff do I have on the reactant side? 7. And look at over here, I only have 4 moles reacting on the product side. So if I'm reducing the volume here, then I'm going to, if I reduce the volume, and this is the thing I'm concerned about, right? Because it's the only gas. If I reduce the volume, it's going to shift to the side with the fewest number of moles. So it's going to shift right, you guys. All right, so then I have the preparation of gaseous phosphorus pentachloride according to the equation. Here's phosphorus pentachloride. One thing I find interesting here is I see that there's 1 mole of this, 1 mole of that for a total of 2, and there's 1 mole over here. Okay. Now I notice that I have less moles of the product than the reactant. And so what is the question asking again? How does the preparation of this product, how is it affected if I, again, decrease the volume? Well, if I decrease the volume, according to Le Chatelier's principles, it's going to shift to the side with the fewest number of moles. This side has 2 because 1 plus 1 is 2, and this side only has 1. All right, let's go ahead and do the last one. The reaction of phosphorus trichloride with ammonia. Phosphorus trichloride with ammonia. So here's my 2 reactants. Everything looks like they're gases. That's good. Now, what happens when I reduce the volume in this particular, for this particular reaction? Well, I look over here and I have 1 plus 3 of a total of 4 moles. And I have 1 plus 3 over here of a total of 4 moles. So each side of my reaction has 4 moles. Therefore, I don't see that any shift will occur because it won't have any effect because both sides have the same number of moles. There will be no stress relief for C. All right, last one. Exercise 15. For each of the following reactions, predict how the value of K changes as the temperature is increased. So make sure you read the problem carefully. One thing I just want to start off is I look at A and B, and this one is a positive value of enthalpy, and this one is negative. So if it's a positive, the first one, A, if it's positive, you can almost consider heat as a reactant. And then let's just do B really quick. If my value for enthalpy is negative, I would consider heat as a product. It's being released. Okay, so let's go ahead and take a look at A. Here, I'll label this for you too. This is endo, and this is exo. Okay, so take a look at this first one. Because the reaction is adding more heat, it's asking us what would happen to the value of K. Value of K. All right, so I think for this one, K is going to be greater than 1. K is going to increase because the reaction is shifted right due to the addition of heat on the reactant side. All right. So I predict that K would get larger for the first one. It would increase. Now, B, I see that heat is a product. And here's what I'm going to say. I'm going to say that the reaction would shift left due to the addition of heat as a product. So, and so K is going to decrease. Okay, so to finish up this last video here, I wanted to briefly talk about something called the common ion effect. Now, I just hope to introduce this concept here, and I'm hoping we can actually touch on it in more detail when we get to our acids and base unit. But ultimately, the common ion effect is going to deal with, at large, solubility and precipitation reactions. And what we find is that we can actually control the amount of precipitate that's forming in a reaction through the common ion effect. Now, this is simply an application of Le Chatelier's principle. And so, again, remember, if you have any chemical reaction like the one here at the bottom of page 11, if we, for example, add more of reactant A in this particular scenario, we would expect that the reaction would shift to the right, which would consequently produce more of the products. Now, one thing before we do the last two exercise problems in the unit here is that it would be appropriate to use capital KSP. So the KSP is going to be the correct signage that we're going to use when we're dealing with the common ion effect. Now, in exercise 16, let's get an idea and look at a larger, bigger picture here of what exactly is the common ion effect. Note that in my reaction, I have solid silver iodide. And when a scientist wants to create more of this solid from the reaction that you see listed, they decide to add an aqueous solution of potassium iodide. Okay, what effect will adding more of the potassium iodide have on this particular reaction? Well, a couple of things to note here is that when you look at the reaction I gave to you, potassium iodide is not indicated anywhere. However, potassium iodide, which of course, as you can see here in the problem, is Ki, it's going to have that iodide ion and would serve to shift this reaction further to the left if we indeed added this to the chemical reaction. Okay, does that make sense? So if we went ahead and added potassium iodide into this reaction vessel, we would get an increase in concentration of the iodide ions. Yes, we would have potassium, but in this case, iodide and silver will form silver iodide. So by virtue of just adding potassium iodide solution, it would cause a greater concentration in iodide ions and therefore allow this reaction to shift left to form more of the silver iodide in solution. So I'm going to go ahead and write that. Okay, now if that's confusing to you, think about it like this. When you put potassium iodide into this system here, you're going to mess up the current equilibrium situation. And when we drive the reaction left more by virtue of putting in potassium iodide, it's going to consequently make more of the silver iodide solid. It's going to make it a lot less soluble. So it's going to make it harder for it to separate into its ions. And this is what we call or refer to as the common ion effect. Let's take a look at exercise 17. The equilibrium constant here for the reaction is 1 times 10 to the minus 28. We have a solution of 0.010 molarity of cadmium bromide, and this was actually thrown into this reaction. You guys, please be clear that we're dealing with cadmium sulfide. So what this problem is telling us is that they are going to go ahead now and just throw in a 0.01 molarity cadmium bromide solution. Okay, it's asking us what would the molar solubility be after adding a solution of this cadmium bromide. Well, this one is a little bit more challenging. You are going to need to set up a Rice diagram. They're talking about something called molar solubility, which hopefully we'll cover in a little bit more detail in the acid and base unit. And so what's going on here is it's telling us that there is an equilibrium constant. And again, because we're looking at this precipitate that forms. We're talking about a KSP of 1.0 times 10 to the minus 28. And it's telling us that they're going to go ahead and add an additional solution of 0.010 molarity cadmium bromide. And this is going to be thrown into the reaction vessel, and it wants us to now calculate the molar solubility after we add this stuff in. Now, before we begin, can you predict what's going to happen here? When we add more cadmium bromide, we're actually going to create and provide more cadmium ions available, which consequently is going to drive the reaction left to produce more of the cadmium sulfide solid, and therefore reduce that salt and make it a lot less soluble. And so when you're given a problem like this, where it gives us the concentration of this new solution being added, we're going to essentially ignore the bromide ion. We're interested in the cadmium because that's actually going to provide the cation to form the solid, right? And since we are adding 0.010 molarity of cadmium bromide, we're actually going to put that over here in the initial concentration on the product side. Okay, and we're going to put 0 for the sulfide ion because we're not changing any of the initial concentration to that. And so what we're going to do is we're going to make, they say then plus X. Go ahead and write your equilibrium portion here. Alrighty, should have done this initially, but writing your KSP would be cadmium 2 plus and sulfur 2 minus. And then we know that our KSP is given to us in the problem, 1.0 times 10 to the minus 28. We're going to go ahead and set that equal now to the equilibrium expressions that we got here. Cadmium, we got 0.010 plus X. And we're going to go ahead and multiply that by X. Now here is the thing, and you're going to see this come up a lot. You see this plus X here, this right here. Turns out that we are actually going to ignore this plus X. Now, this is because if you look at the current KSP, it is so small that we should actually expect X to be small as well. And if you take 0.010 molarity and you add that to an already really small number, you're still going to have a number that is close to 0.010. And so in this particular case, we do not have to actually include this in our calculation, and we'll simplify things a lot more. Now, when you solve for X, you should get 1.0 times 10 to the minus 26. And so this would be the molar solubility now, adding in this new cadmium bromide solution. All right, you guys, this is going to go ahead and sum up the unit for now. More to come later on this topic. Thank you so much for watching. Until next time.